Hello, welcome to Astronautics for Exploit. This is Dr. Ayenshola Ogundele. Asteroid collision avoidance, prevention against asteroids' potential destructive impacts. The focus points of my presentation are as follows: asteroid collision avoidance and asteroid collision avoidance approaches. Earth's history. The history about the development of the planet Earth from the period of its formation to the present day period has been tremendously shaped by various astronomical events which have contributed immensely to the better understanding of the past events of the Earth, biological evolution of life, formation of the Earth-Moon system, and a host of others. According to history, several asteroids and meteor airbursts have impacted the Earth, with some of them causing destruction of property, injuries, and even death. On June 30, 1908, an explosion attributed to a meteor air, the atmospheric explosion of a stony asteroid about 50 to 60 meters occurred and was reported that it leveled several thousands of square kilometers of forest in a very sparsely populated area. This is referred to as Tunguska event. Asteroids impacts on Earth could occur in future. To prevent its future occurrence, various planetary defensive measures are being taken. Asteroids impact avoidance, a future prevention strategy, involves development of methods which will help to divert near-Earth objects that are on a potential collision course with the Earth and prevent their destructive impacts, which could cause tsunamis or firestorms. Some of the asteroid collision avoidance approaches are kinetic impactor, ion beam shepherd, asteroid laser ablation, focused solar energy, nuclear explosive, mass driver, asteroid gravity tractor, and use of conventional rocket engine. Kinetic impaction involves sending one or more large, high-speed spacecraft into the path of an approaching near-Earth object in order to deflect an asteroid into a different trajectory, steering it away from the Earth's orbital path. An ion beam shepherd is a concept in which the orbit and or altitude of a spacecraft or a generic orbiting body is modified by having a beam of quasi-neutral plasma impinging against the surface to create a force and or a torque on the target. Asteroid collision avoidance. Asteroid impact avoidance comprises the methods by which near-Earth objects on a potential collision course with Earth could be diverted away, preventing destructive impact events. Artist's impression of an asteroid impact on early Earth is shown in this picture. An impact by a sufficiently large asteroid or other near-Earth objects will cause, depending on its impact location, massive tsunamis or multiple firestorms, and an impact winter caused by the sunlight blocking effect of large quantities of pulverized rock, dust, and other debris placed into the stratosphere. This picture shows illustration of asteroid eros. Kinetic impaction strategy. While the chances of a major collision are low in the near term, it is a near certainty that one will happen eventually unless defensive measures are properly taken. This picture shows illustration of asteroid deflection strategy. Asteroid collision avoidance approaches. A number of approaches have been proposed for preventing collision of asteroids with the Earth. Some of these approaches are kinetic impactor, ion beam shepherd, asteroid laser ablation, focused solar energy, nuclear explosive, mass driver, asteroid gravity tractor, and use of conventional rocket engine. Kinetic impactor. Kinetic impaction involves sending one or more large, high-speed spacecraft into the path of an approaching near-Earth object in order to deflect an asteroid into a different trajectory, steering it away from the Earth's orbital path. A small scale was demonstrated by NASA via the Deep Impact mission of 2005. This picture shows a schematic diagram of enhanced asteroid deflector. The impact of a massive object, such as a spacecraft, or even another near-Earth object, is another possible solution to a pending near-Earth object impact. An object with a high mass close to the Earth could be sent out into a collision course with an asteroid so as to knock it off its course. This picture shows demonstration of kinetic impactor. Asteroid deflection. Kinetic impact technique is being planned to be able to deflect asteroids, which may present some risk of collision with the Earth. Research findings show that the chance of an asteroid impacting Earth is very small, but a relatively small asteroid of about 500 feet across carries enough energy to cause widespread damage around the impact site. This picture shows asteroid impact mission. NASA's Double Asteroid Redirection Test is the first mission launched in November 2021, which was designed to demonstrate asteroid deflection using a kinetic impactor. The purpose is to detect and track potentially hazardous asteroids and to study technologies to mitigate or avoid impacts on Earth. This picture shows illustration of double asteroid redirection test. That mission will test kinetic impactor technology by targeting a double asteroid that is not on a path to collide with Earth and therefore poses no actual threat to the planet. The system is composed of two asteroids, the larger asteroid Didymos and the smaller moonlet asteroid Dimorphos, which obeys the larger asteroids. This animation shows the demonstration of that mission strategy. Ion beam shepherd is another asteroid avoidance technique. An ion beam shepherd is a concept in which the orbit and altitude of a spacecraft or a generic orbiting body is modified by having a beam of quasi-neutral plasma impinging against the surface in order to create a force and/or a tug on the target. IBS is a contactless asteroid deflection technique. This picture shows an artist's rendering of Osiris collecting samples from asteroid Bennu. The method of ion beam shepherd involves the use of a low divergence ion thruster pointed at the asteroid from a nearby offering spacecraft. Gravity tractor. The momentum transmitted by the ions reaching the asteroid surface produces a slow but continuous force which can deflect the asteroid in a manner similar as the gravity tractor but with a lighter spacecraft. This picture shows illustration of Osiris spacecraft attempting to retrieve samples from asteroid Bennu. Applications of the ion beam shepherd. The fact that the beam can be generated on a shepherd spacecraft placed in proximity of the target without physical attachment with the latter makes it useful for space applications such as space debris removal, asteroid deflection, and space transportation. This picture shows ion beam shepherd concept. Another approach is asteroid laser ablation. Asteroid laser ablation is a proposed method for deflecting asteroids. involving the use of a laser array to alter the orbit of an asteroid. Laser ablation works by heating up a substance enough to allow gaseous material to eject, either through sublimation, solid to gas, or vaporization, liquid to gas. This picture shows concept diagram of an orbiting D star engaged in multiple tasks, including asteroid diversion and visualization of laser beam. For most asteroids, asteroid laser ablation occurs between temperatures in the range of 2700 to 3000 Kelvin. Thrust for changing trajectory. The ejecting material after the laser ablation creates a thrust, which over an extended period of time can change the trajectory of the asteroid. This picture shows an artist's illustration of a large asteroid heading towards the Earth. Asteroid laser ablation is a promising method. Laser ablation is a promising method because it allows an asteroid to be redirected without breaking the asteroid into smaller pieces, each of which may pose its own threat to Earth. The nuclear impactor is another proposed method for deflecting asteroids, but is less promising than laser ablation. This picture shows demonstration of a concept spacecraft using gravity to tow asteroids away from a collision course with the Earth. Laser ablation is already being experimentally tested in labs as a method for asteroid deflection, and there are plans to begin testing on the International Space Station and in low Earth orbit. This picture shows an artist's impression of a giant space rock. The principle of operation of asteroid laser ablation are: a laser array is focused on the target asteroid. The laser hits the surface of the asteroid to extremely high temperatures, and material on the surface of the asteroid is ablated and ejected away from the asteroid. This picture shows illustration of asteroid deflection strategy. Other principles are: as the material becomes a gas, it is pushed away from the asteroid, and by Newton's third law, it also pushes back on the asteroid with an equal force, called a thrust. Although the thrust on the asteroid is tiny in comparison to the asteroid mass, but by Newton's second law, there will still be some small acceleration. This picture shows a depiction of laser ablation, which involves slowly breaking down an asteroid using a giant laser. Over time, the small acceleration on the asteroid significantly alters its trajectory. Once the asteroid is no longer on course to collide with Earth, the laser can be removed. Deflecting an asteroid using laser ablation will likely take between 1 and 10 years, depending on a number of factors. This picture shows an illustration of a rocket approaching an asteroid that is drifted too close to Earth. Focused solar energy is another approach. Researchers proposed deflecting an asteroid or comet by focusing solar energy onto its surface so as to create thrust from the resulting vaporization of material. Focused solar energy method will first require the construction of a space station with a system of large collecting concave mirrors similar to those used in solar furnaces. This simulation shows artists' impression of asteroid deflection using an innovative ring array solar collector. It was reported that orbit mitigation with highly concentrated sunlight is scalable to achieving the predetermined deflection within a year, even for a global threatening body, without prolonged warning time. Conventional concave reflectors are practically inapplicable to the high concentrated geometry in the case of a giant southern space target located in front of the mirrored surface. This picture shows planetary defense by high-powered laser. Material ablated off a would-be impactor alters its trajectory by conservation of momentum so as to avoid an impact. The positioning of any collector at a distance to the target much larger than its size will not yield the required concentration level and therefore temperature because of the natural divergence of the sun rays. Intensive ablation of the rotating asteroid surface under this focal spot will lead to the appearance of a deep canyon which can contribute to the formation of the escaping gas flow into a jet-like one. This picture shows NASA's Lucy mission, which will be the first to visit the Trojan asteroids. Ring array collector. It is assumed that intensive ablation may be sufficient to deflect a 0.5 km asteroid within several months and no additional warning period. For such a prompt deflection of the larger neos, the required collector size are comparable to the target diameter. This picture shows an artist's rendering of NASA's near-Earth asteroid rendersfall spacecraft at asteroid Eros. Nuclear explosive is another approach that is being proposed. Nuclear explosive. Initiating a nuclear explosive device above, on, or slightly beneath the surface of a trailing celestial body is a potential deflection option, with the optimal detonation height dependent upon the composition and size of the object. Nuclear explosive method does not require the entire neo to be vaporized in order to mitigate an impact threat. This picture shows 1984 Strategic Defense Initiative concept of a generic space-based nuclear reactor. Depending on the energy of the explosive device, the resulting rocket exhaust effect created by the high velocity of the asteroid's vaporized mass ejector, coupled with the object's small reduction in mass, will produce enough of a change in the object's orbit so as to make it miss the Earth. A hypervelocity asteroid mitigation mission for emergency response has been proposed. This picture shows artist's illustration of the DART spacecraft aiming to smash into the asteroid Dimorphos. Mass driver is another approach that is being proposed. A mass driver is an automated system on the asteroid to eject material into space, thereby giving the object a slow, steady push and decreasing its mass. A mass driver is designed to work as a very low specific impulse system, which in general uses a lot of propellant but very little power. This picture shows a conceptual image of NASA's Orion spacecraft approaching a robotic asteroid capture vehicle. The main idea of mass driver is that when using local material as propellant, the amount of propellant is not as important as the amount of power, which is likely to be limited. This picture shows illustration of asteroid Eros' southern hemisphere. Asteroid gravity tractor is another approach of asteroid collision avoidance. A gravity tractor is a theoretical spacecraft that would deflect another object in space, typically a potentially hazardous asteroid that might impact Earth without physically contacting it, using only its gravitational field to transmit the required impulse. This animation shows illustration of asteroid direct mission vehicle conceived to demonstrate the gravity tractor planetary defense technique on a hazardous-sized asteroid. Using gravity tractor, the gravitational force of a nearby space vehicle, though small, can alter the path of a much larger asteroid if the vehicle spends enough time close to it. All that is required for gravity tractor is that the vehicle thrust in a consistent direction relative to the asteroid path, and that neither the vehicle nor its expelled reaction mass come in direct contact with the asteroid. This picture shows gravity tractor for asteroid deflection. The tractor spacecraft could either hover near the object being deflected or orbitate, directing its exhaust perpendicular to the plane of the orbit. Advantages of the asteroid gravity tractor are: nothing needs to be known about the mechanical composition and structure of the asteroid in advance. The relatively small amounts of force used enable extremely precise manipulation and determination of the asteroid's orbit around the Sun. This picture shows asteroid redirect vehicle conducting a flyby of its target asteroid. Another approach is the use of conventional rocket engine. Attaching any spacecraft propulsion device will have a similar effect of giving a push, possibly forcing the asteroid onto a trajectory that takes it away from the Earth. This picture shows illustration of the impact of the DART double asteroid redirection test projectile on the binary asteroid system. An in-space rocket engine that is capable of imparting an impulse of 106 Newton seconds will have a relatively small effect on a relatively small asteroid that has a mass of roughly a million times more. This picture shows SRS-era mission for planetary defense. For more information, contact Astronautics for Exploit. You've been watching and listening to Asteroid Collision Avoidance, Prevention Against Asteroid Potential Destructive Impacts, with the focus points Asteroid Collision Avoidance and Asteroid Collision Avoidance Approaches, presented by Dr. Ayansola Ogundele. Thank you.